Okay, so yeah, so chapter 4 is all these sort of, not too deep, but cool applications of Fourier analysis to things that you might not expect, to areas where you might not expect it to show. Okay, so the first example is this thing called isoperimetric inequality, and it's basically a statement about simple closed curves, right? It's saying that basically that the curve which holds the most area is what you expect, right? What curve would should hold the most area? Well, the circle, right? The curve of a fixed length, right? Suppose somebody gives you a wire and says, okay, I'd like you to enclose as much area as possible. The answer is a circle, so obviously not an oval, right? But why is that true? It turns out that we can prove it using Fourier series. Whenever I say the word wire, I'm reminded of my old calculus math teacher who was from Boone, North Carolina, and he would say, "Suppose you've got a wire." Suppose you've got a wire. And he'd say, "A what?" He'd say, "A wire." Anyway, so basic knowledge, as usual, Stein will give you some basic knowledge that everybody should know, and this stuff really is stuff that you all should know. Top 3 knowledge, but let's quickly review it. Right? So you have a map gamma into R2, right? And let's say that one gamma is C1, right? It's continuously differentiable, and 2 gamma prime is not 0, right? Okay, and then this gamma is called parametrized curve. Parametrized curve, right? And the image of gamma, which we'll call big gamma, is called curve. Parametrized by no gamma. Right, and then there's these other notions. Simple curve, right? Simple curve means it doesn't intersect itself, and closed curve, so it doesn't intersect itself in the interior AB, and closed means that gamma of A is gamma of B. Right? It starts and ends at the same place, right? Right. So starts, closed just means that it starts and ends at the same place. Simple means that it cannot intersect itself, although it could intersect itself at the very end. Right? What's wrong with you? Where are you from?
That's related to some other thing.
Okay. Right, and the point of this smoothness is to ensure, and the point of this requirement is to ensure the existence of a good tangent vector. Okay, this is to get so we have a non-zero tangent vector. Okay. Second definition. Right. If you have a curve gamma, big gamma, parametrized by little gamma, which has maybe component functions x and y, then we define the length of gamma as the integral of the size of the C. Right? In other words, the integral from A to B of x prime squared plus y prime squared 1/2. That's the length of the curve. So you should be having like flashbacks back to calculus 3. It's old knowledge for you. But let's just remind us. Okay. If we have another function, say s, oops, got backwards, CD, AD, right? We have a bijective, again, C1 map. Then we can define eta as gamma composed with S of T. Right? And right, so this is going to be a map. Eta is going to go from CD then into R2. And you see that it has the same image as gamma. Right? It's got the same image as gamma, little gamma. Right? It will give you just the same. This is another parametrization, a reparametrization of big gamma. This is called a reparametrization. Big gamma. Okay. And it's an easy exercise involving the chain rule to notice that length is independent of parametrization. If we take a reparametrization and look at the length of the reparametrized guy, we can still get the same length. Right? If the speed is 1 throughout, for this reparametrization, we call eta the arclength parametrization. Right? So like these parametrizations, you have this dot, and it's basically walking along the path. Right? And it's always possible, it's an exercise, I think, using the fundamental theorem of calculus to see that it's always possible to create a function that to create a parametrization that walks along the path and walks at a speed of 1. Okay. It's an easy exercise. I think it's a homework exercise. So that parametrization is called the arclength parametrization, and we'll use it. Okay? We'll use the fact that we can always get an arclength parametrization. Okay. Everyone all right? You should not be all right. You should be bored. You should be bored. You should say, why is Professor O doing calculus 3 again? That's what you should say. Okay, so now we're going to make a reckless definition. We define, so let gamma be a simple closed curve. Gamma is a simple closed curve. And let's say, again, parametrized by little gamma being x, y. We define the area enclosed, the area of the region enclosed, by big gamma this. The area is 1/2 the integral from a to b of x as x y prime minus y x prime ds. So, does anyone remember this formula? Maybe you remember this formula. This is actually a consequence of Green's theorem. Okay, this is a consequence of Green's theorem. This is not how one defines area, of course, right? Like if you went to a child and you said, I'm going to define the area of this thing in a circle by taking the parametrization and then creating this integral, blah blah blah. And that's what I'm going to call the area. Okay, so we're doing this so that we don't have to prove that this actually is the area. Okay, so we're shoving everything back under the rug of Calc 3, of Green's theorem. Right? So we don't have to explain Green's theorem again. Anyways, consequence of Green's theorem. Okay, but to define area in this manner is, pretty reckless. It's just as if you define area under a function by saying, oh, I'm going to define the area of this function as the difference of the antiderivative of the endpoints, right? Like if you said that to a kid, right? Oh yeah, that's how we define the area of this thing. Just you take the antiderivative of the function and then take the difference of the endpoints. That would be an equally, pedagogically wrong thing to do. So in any case, but in any case, this is how we're going to define area. Okay, so that's the end of the review. Knowledge that you should have should be familiar to you already. So now let's go to the isoperimetric inequality. Okay, so here's the theorem. You've got in R2 a simple closed curve, and it has length L, and A is the area of the enclosed region. And that actually opens another question. If you have a simple closed curve, how do you know that it actually encloses a region? That seems like an obvious thing, right? That a simple closed curve encloses a region. But how many of you know that this is not at all an obvious question? This is actually not at all an obvious question. To answer it, you need to use algebraic topology, something called the Jordan curve here, the Jordan curve here. So, Jordan curve here. Okay, so you've got this simple closed curve. You've put numbers on. You've given names to the length of the area. Then the area is controlled by L squared over 2 pi. That's great. That's pretty cool, right? L squared over 2 pi is the best you can do, and you have equality if and only if gamma is simple. Okay, so let's get going. The proof of this is pretty cool. It's just using parsible's identity over and over and over. Okay, so we start off by just assuming without loss of generality by scaling these assume that the wire we're given is of length 2 pi. So we're going to show that the maximum area we can get is 2 pi, and that we only get that when we have a circle. Okay. So here we go. Take the arc-length parametrization. Take the arc-length parametrization gamma. Right. Because it is the arc-length parametrization, we know that 1 over 2 pi right, of x prime s squared plus y prime s squared ds is 1. Is that right? Can I see some of these books for a second? I'm excited to do something so embarrassing, but something's bothering me. Yes, of course. Sorry. Yes, of course. Yeah. Okay. Right, because this is the right. This is the size of the tangent vector squared, right? The size of the tangent vector is 1. Right? So we're integrating 1, we get 2 pi. Divide by 2 pi, we get 1. Okay. So right. In other words, if we write this in the L2 notation, this says that right, that the x prime the L2 size of x prime squared plus the L2 size of y prime squared is 1. Right? Okay. That's what it says. Right? Using the L2 notation. So x and y are 2 pi periodic functions. With Fourier coefficients. Let's denote the Fourier coefficients a sub n and b sub n. And x prime, y prime have Fourier coefficients I n, a sub n, I n, p sub n, right? As we saw in the last chapter using integration by parts. Right? There's a relation between the Fourier coefficients of the function and the derivative of the function. Okay, so we can use Parseval. Right? By Parseval's identity. What do we get? Well, here is the L2 norm of the derivative squared. So what is that? What does that turn into? The Parseval's inequality, Parseval's identity. Parseval's identity, which you should know in 2 days' time. It's the little L2 norm of the sequence, right? Squared. Right? So we've got this thing, right? This thing turns into corresponding thing for the little L2 norm, right? So we have I n, A n, the sequence in little L2 squared, I n, B n, little r2s. That's what parsable tells you. Right? So, in other words, we get that summation n squared an squared plus bn squared as everything is over z as well. Because the little ulterior norm is the sum of the squares of these guys. Everything is square rooted, but the square root cancels. It's still up by 2. So we get the sum of the squares of these guys. Right? You put them together into this. Okay. So that's the first thing we do. We take the statement about the arclength parametrization and we translate it into a statement use Parsifal's identity to translate it into a statement about the Fourier coefficients. Okay, everyone all right? Okay, so now we take our definition of area and we do the same thing. So the area is by Tony definition. 1/2 that's the value of the integral from a to b of x y prime minus y x prime. Right? And now we use parsibles again. Right? This thing here is the inner product. Right? This part here is the inner product of x against y. Well, if we put a 1/2 pi. Right, so here we've got the inner product of x against y prime. Here we've got the inner product of y against x prime. And so we use the Parsifal's identity, the polarized Parsifal's identity again. Right? Right? It's an inner product, so we can use the polarized Parsifal's identity. And we end up with this being I times summation n a n b n bar minus a n bar b n. Is that right? That's fine.
Why are we integrating from A to B?
So that should be from 0 to 2 pi first off, yeah. Right. And did I miss this up? We're going to get an against the conjugate, right? So we get negative. Wait, something is wrong, right? Is that-
Get those right.
Right, this should be, right, so we're taking the inner product of the base ANs, right, against the guys for y prime, right? Y prime is IN, BN, right? Minus, again, the IN, BN, no, the BN against the x prime guys. Right, we should get pi times that. Right. So this thing here is summation a sub n times the conjugate of this thing. Okay, so we get negative I, right? Negative I and Bn, right? With the Bn with a bar over it. And then here we get just put it all together, we get Bn times negative I and An. Times that. Right. Okay. 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 In any case, we get that this thing is bounded by the sum. This is what I should have done. I'm just going to use the triangle inequality. So this, it's bounded by the sum of f sub I and n, a sub n, b sub n, minus a sub n. That's okay. Okay. So, okay. So, right, Parsifal's identity, we use Parsifal's identity again on what the area is, right? We translate Parsifal's, translate the definition of area into a statement about the Fourier coefficients, and then we go onwards. We're going to put everything together and see that this must be less than or equal to pi, right? So, right. So our goal is to show that this line this thing is less than or equal to 1. And if we do that, then we've got the first part of the isoperimetric inequality. Okay. This part actually is a consequence of this. You notice that these things are sort of similar, right? And maybe you see what we need to do. You just observe. You make an obvious observation that this thing here, in this case, bar p sub n, is less than or equal to twice a sub n, b sub n, which is less than or equal to an squared plus an squared. Okay. So you do something very crude, right? We use the triangle inequality here. Right? Use the triangle inequality here in a very crude manner. Killing off any cancellation, offending people who like sharpness. And then we do something here. What's this? This is the quadratic. This is just the observation that an minus bn quantity squared is positive. Right. Right. This inequality is just this observation. And so you notice a couple things, right? That we okay. Sorry, let's go onwards and we'll go backwards. Okay, so that's it, right? Right. This thing here we see is say, well, this thing which we wanted to bound by 1 is clearly bounded above by n times an squared plus b n squared, right? By the statement we just said, by the simple observation we just made, right? And certainly it gets even bigger if we put in a square here, right? It gets bigger if we put in a square, and now we see that we've got 1. Okay, so that's the proof of the first part of the isoperimetric inequality, that the area is got to be bound. If your wire is 1, 2 pi, then your area is bounded by pi. So now we have to answer the question, why is it that that circle is the best thing, right? Certainly the circle is a good thing, right? We do get the maximal area when we use the circle. Why is it the only thing that gives us the maximal area? And for that we have to look a little bit more back at this thing and think, well, at what point could we have equality, right? Well, this thing would have to equal, this would have to be an equality, right? This thing would have to be an equality. Further, our n could only be 1, 0, or negative 1, right? Because once we get to 2, that is, we can't have terms for n bigger than or equal to 2, because if we did, when we square this thing, we'd be increasing the size, right? So we'd have no chance of getting an equality. Okay. So those are the first 2 observations we made, that to have equality, so the argument to show that we only get a circle is a little bit a pain, but it's sort of cool, I guess. So why does an equal pi imply that gamma is a circle? Okay. So first, observe that we cannot have any terms a and b n for n greater than or equal to 2, right? Because if we did, then we would lose all hope of having equality. Right? When we square that n, we lose all hope. Squaring n, lose all hope. Forget that. Okay, so in that case, let's put down some notation. Xs has to be j minus 1 e to the minus s plus a naught plus a1 e minus. Ys would have to be b minus 1 e plus b naught plus b1 e minus. Okay. So let's see. We know that since x and y are real valued, a minus 1 is a1 bar, b minus 1, b minus 1 is b1 bar. Right? Okay. And so if we look at this thing, right? If we look at this thing, what does that tell us? Let me put the star on this. Right? So we have only terms for 1, 0, and minus 1, right? So consider, look at star. Look at star, what does it say? It says that A1 squared plus B1 squared. And then we have the negative guys as well, but they have the same size, right? So we get two of those guys. And we have the zero terms, so we multiply by 0, so we get 0 of that, so we get 1. That star for us is this statement. Right? Because we have, right, we've got the minus 1, A minus 1 squared plus B minus 1 squared plus 1 A1 squared plus B1 squared. Right? But we just noted that those have the same signs, right? So we get this. Okay. So that tells us that A1 sorry, I'm not saying anything yet. Okay. So here, we also have from here that so equation 2, we know that 2A1 B1 must be A1 squared plus B1 squared. Right? Right? And right? So for some reason that I've forgotten, then you can, so this implies that A1 and B1 are the same size. Why is that? Why is that? I'm sorry, I'm sort of slipping my mind. We know that's true, right? That thing on the right is a half, right? This thing on the right is a half, right? So we get A1, B1. Why are the sides of A1 and B1 the same? Oh yeah, of course, yeah, because the size of right. Because this is equal to 0, right? Yeah, thank you. Sorry, I just went crazy. Right. So they're the same size, right? So size of A1 is so these guys are the size of 1/2, right? And so that tells us that A1 looks like this, right? Is a half e to the I alpha. B1 is also a half e to the I beta. Right? And since we have 1 equals 2 A1 B1 minus A1 bar B1. This is the same thing in this notation. This is the same thing as saying that 1/2 e to the I alpha minus beta minus e to the minus I alpha minus beta equals 1. And so that's the same thing as saying that the sign, the absolute value of the sign of alpha minus beta is 1. So, blah, blah, blah. Alpha minus beta must be k pi of 2 for some k. Right? And in the end, you get that x must be alpha naught plus cosine alpha plus x, and y must be b naught plus or minus sine alpha plus x, which is So the only way that we get the maximal area is this. I think the more significant part of this is actually the first part. The second part, showing that you get this, that you need to get, you have to have a circle that's sort of cool, but not maybe. I think the more interesting thing is how we apply Parsifal's identity to get the bound. Any questions about that? Any questions about that? So we have an exam on Friday. Not to say that I would normally do this, but I made a list of topics that may be helpful for me. Not to say that I'll ever do this again, but I made a list of definitions and concepts, theorems, and derivations. So for example, if I ask you what a good kernel, so at the very beginning of the exam, I haven't finished making the exam, but roughly speaking, I think it'll look like this. It'll be a section on definitions. So just like, what's the Fourier coefficient? You should be able to tell me what the Fourier coefficient is. What is a César sum? What's that? Right? What does it mean for function to be Helder continuous? Lipschitz, I forgot to put Lipschitz continuous. Please add Lipschitz continuous. So that's just a type of Helder continuous. What's a good kernel? Right? Good kernel is in capital letters. Right? This is one. So, and that's not going to take very much time, right? Because that'd be a waste of time for you guys to just spew out definitions. So a few definitions, just to make sure you know what the terms mean. And then I think what I'm going to do is have a true-false section. But the true-false will be a little bit tricky in the sense that you'll have to tell me why, right? So it'll be true-false, but explain why or why not, right? Why it's true. This is true by such and such thing. This is false because we know blah, blah, blah. This will be, and it could be involve like one step, say. It could involve like, some way, you need to understand, how the theorem, you need to apply the theorem, say. This is true because blah, 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 using blah this theorem. Okay, so there'll be like a slightly more in-depth true-false section. And then after that, I think there'll be a section on, so what I'd like to do, the knowledge that I think you all should have is the following sort. One, you should be able to tell me roughly how an argument goes, right? Like if I say, well, how do you prove that convolution the convolution of two functions is continuous, right? You say, okay, so roughly speaking, I want you to give sort of like a rough argument, and then also details, right? So that is, you should have your knowledge on sort of two scales, right? Like a rough way of you should know roughly the argument, and you should also know, the proof of some key details. So I think what's good practice for you guys is to go through and think for each thing that I've listed here, what's the key step? What's the key step? Because I may ask you to prove that key step. Okay, right? Like, in proving the properties of convolution, we use, over and over, we use the L1 approximation method, right? It's almost guaranteed I'm going to ask you to use the L1 approximation limit to prove some result, right? To go from a result about a continuous function using the L1 approximation limit to a result about integral functions. It's almost, it's almost like I can't avoid it, right? So this sort of thing, right? So look through the theorems and say, what's the key step, right? What's the key step? Do I understand that key step? Right? What's the technique involved? Because that's, you need to be able to, in your knowledge, you need to be able to say whether something is true or false. Like if somebody asks you, oh, is it true that if you have a Fourier series and coefficients converge like blah, that the function, that the Fourier series converges to the function? Right? And you say, well, because I get asked this all the time, right? And you go to a conference and they say, you're a harmonic analyst. Okay, well, we have this question, and your knowledge needs to be of the sort that you can actually, you say, I think this is true for such and such a reason, right? Or false for such and such a reason. Right? That's the true, that's called the true-false business, right? And you also need to be able to have access to this bunch of techniques, right? L1 approximation, it gives you results about integral functions. Other, best approximation lemma, this is so that's what I want to say about the example. And like I said, I don't hope to make it a tricky example. I don't hope to make it a tricky example. I rather want to test you on fundamentals. So you don't have to be clever, but you have to master the craft. You don't have to be artistic. You have to be craftsman.
Can you hold on to the homework for Friday?
Yeah, sure. Yeah, if you like. Yeah, if you like.